Oh, it started. But did the second monitor turn on? All right. Keep going. Our exam is on Monday. We will see how much we go, how far we go with it. This one definitely has definitions on it, and it has probabilities, more calculating and stuff. So we had the homework due today. Is it all of the homework? I can't remember. When's that assessing normality due? And that was a screw up on me. I meant to upload the data file. Kind of completely forgot. Let's check this out. Okay, so normal probabilities. Yeah, it's due today. I've got that set at 5 o'clock, so you should be working through that. That's a mixture of doing things by hand, using R, and so forth. So that kind of gives you a preview of what you might see on the exam, including, the closed book portion of it is maybe calculating some normal probabilities using the table. If you have your normal tables, you can bring it and use it. I'll have some available, and I can always print more. The assessing normality is I have for later tonight. I'm flexible on that due date, but try to get things done so I can get the key posted, because we know that both of these things are going to be on the exam. Next question is, what else? What else will we have on that exam? Also on the homework, you can see that we have. I do have some like extra homework and probability problems. That's optional. Ooh, 2019. Let's change that. $11, 18, I guess. All right. So we'll change that to next week, Monday, if you choose to do it. And again, this optional homework is meant to kind of give you extra practice on probability. This is stuff that you can do by hand. All right, you can use R for it. Same thing here, like the binomial probabilities, the Poisson distributions. I say practice answering these questions by hand and use R to confirm the answers. We haven't really learned how to do them by hand. And I gave you the equations, gave you the code for using the calculator, but yeah, use your R, and this should kind of help you out, help prepare for the exam. It's optional; you don't need to do it, but it's there. If you sit down and do that stuff, and you're like, "Yeah, this is pretty easy," you'll probably be okay. Other than the definitions, make sure you look over the definitions. All right, so we are finishing up this. Assessing normality. I need to load my car library. And then I'm going to go down to the practice. Load the normality data so I have access to it. And then for questions 5, 6, 7, and 8, we went ahead and made our own vectors. Called them Q whatever, based on the number. or based on the header, all right? And what we used was that na.omit function, where na.omit goes through and strips out all of the missing data rows. So any row that has missing data, na.omit strips it out. Usually you don't do this for a data frame. Usually this would be individual variables that would be removed. It's on a case-by-case basis, basically. But for here, we're assessing normality of each individual. No problem with using na.omit on the vector that is found inside the data frame. So we've got Q5, Q6, Q7, Q8. And for Q5, we checked our histogram and normal curve. And I asked you to check everything else out, right? QQ plots and Shapiro-Wilks. So what is QQ plot? We already have Q5 made. So you should have something like this, curved. Pretty obvious, non-normality. I think the histogram is pretty obvious too. Huge number of data points, it's skewed. And I'm not going to be surprised if Shapiro.test comes up to be the same way. Yep. So P is less than 2.2 e to the negative 16, which you will hear numerous times. It's the smallest p-value that R will report. So that's the smallest p-value. All right, question 6. Q6. All right, so Q6. Here's what I am going to do. I'm just going to copy all of these. So we are doing hist of the Q6, Q norm, or curve of the D norm. Going to use QQ plot, Q6, and Shapiro.test, Q6, so all in one chunk. Typically, this isn't what you would do in your exam. I'll have a separate chunk for each test. So here's Q6. What do you think for the histogram? Normal, non-normal? Normal-ish. What's the problem that we have? Yeah, not just missing. I think this kind of gives it to us a little bit better. We don't have a huge number of data points. We actually have a fairly small sample size. And if we look at Q6, we've got 20. So right over here, I can see that we have 20. Let's move that over. Up in the environment, we have 20 data points. So with 20 data points, it's kind of hard to utilize. Not kind of hard. It is hard to utilize any sort of histogram with normal curve overlay to even come up with a determination if it's normal or not. If we look at Shapiro-Wilk normality test, p-value is 0.1158. It looks like it's normal, but again, at these small sample size, Shapiro-Wilk will really have a hard time detecting any non-normality. So because of that, we should be leaning more towards these QQ plots. Now, there are a couple points that are outside the line. These are at the extreme. All right, and we'd say we could kind of set up, well, 5% maybe is what's allowed. 5% in the extremes is what we could allow, and out of 20, we're outside of that. We've got 3, right? So we've got more than 10% that are outside of this. What, 15%? But that's okay. With a small sample size, you're going to see something like this because these probabilities, or the probability of getting data points to these extreme, are going to be low, but they're going to be they're possible. And if you get them, they fall out like this. We don't have a huge number to help offset those. So it's possible that we are missing these values in the middle, like we saw in the histogram. These values, we're missing them. These might be like in the 10-15% range, maybe 20% chance that we'll have these values, which is somewhat high, but we don't see them. We don't see them here. So I look at this, I look at the QQ plot. This looks pretty good. all but the end points are out. And not only that, any of these points that have a number attached to them, this is R's way to tell you these might be outliers. These might be unusual data points, and you might consider excluding them from your analysis. Do we exclude outliers? No. There's only a couple of special cases when we exclude them, but it's enough to say, I'm not worried about these points. All right, that's question 6. Do question 7, or vector 7, I should say. I'm going to update all of these. Make use of copy and paste functions. All right. Same type of issue. We've got bars. If you try to increase your bars, you're going to have even more gaps. And this is because Q7 only has 10 data points in it. Shapiro-Wilk is going to be hard to detect. Again, it suggests it's normal. Maybe it is. So about the only thing that we can rely on is a QQ plot. What do you think? Does this look okay?
Looks a little curved.
Yeah, it looks a little curved. Are points inside the 95% confidence interval? Yeah. I think this is good enough. Again, this is sample size of 10. Sample size of 10. Getting an extreme value, slightly extreme value, entirely possible. Yeah, it kind of looks curved, but we're in the confidence interval. Almost all of our points are in there, except the ends. Now, if anything in the middle was outside, yeah, that's not normal. But if all of the middle points are in here, it's good enough to call it normally distributed. All right. And our last one, Q8. Q8. Wait. Q8. All right, we got a little bit better. We've got 60 data points. That's our histogram, and again, I could adjust the Y limit, make sure it looks a little bit better. What do you think? Yeah, hopefully you're seeing histograms aren't the greatest. Histograms aren't the greatest. Shapiro-Wilk does detect non-normality. At 60, I'm hesitant to use it, but at a small sample size, it's much more likely that Shapiro-Wilk fails to detect the non-normality. So if it detects the non-normality, and with a sample size of 60 or a sample size between, let's say, 50 and 100, there's probably a good chance that this is non-normal. And I look at this, here's our problem. All right, Shapiro-Wilk gives p-value 0.03681. Our QQ plot looks something like this. Kind of looks S-shaped, right? But we can't just rely on the curvature. All right, we can't just rely on the curvature. Yes, I look at that curvature and say this looks non-normal, and coupled with the Shapiro-Wilk, I might say, yeah, this could be non-normal, but based on the QQ plots, we got these ends that I'm okay with. This point's questionable if it's outside of the line. This point's outside, that point's in. Again, the extremes I'm not so worried about, but the bulk of our data points are inside of that confidence interval. So I think just by the QQ plot, I'd say I think it's normally distributed. I think it's normally distributed. Fortunately, most of the tests that we run are fairly robust violations of normality. So even if this is slightly non-normal, that's okay. ANOVA is going to work just fine with it. All right. So this is a situation where the histogram kind of looks like it might be non-normal. Shapiro-Wilk says it's non-normal, but the QQ plot is arguing for normality. Questions? Isn't this fun? It's like, maybe it is, maybe it isn't. You'll get some that are kind of these questionable. I want to see here. I want your interpretation. So, on a question on the exam that might ask, is it normally distributed? And I would ask, provide an explanation for your answer. Then you could say, yeah, this looks normally distributed because all points are inside the confidence interval. Or you could say, maybe it's not because we have excessive number of points outside the confidence interval. Or you could say, we've got some points outside, but Shapiro will suggest it's non-normal, so I'm going to go with the non-normality of this, as long as their sample sizes are adequate. But we'll judge based on your interpretation. Did you do the interpretation correct? Are you looking at the correct things? Questions? No? Yes? Save that. All right. So I had the rest of this presentation, which was basically the same thing. Just these figures. Let us continue. All right. So we've been introduced to these distributions. Discrete and continuous distributions. We have to understand those. We had to understand how to calculate these probabilities because those probabilities are going to be used in our hypothesis testing. So what this presentation is kind of like an introduction to the hypothesis test. I mean, there's more introduction than there is actual doing the hypothesis tests. But what we're trying to do is link our distributions that we've been talking about to a p-value. So this was in chapters 7 and 9 on the OpenStax book, if you were curious. All right, so why do it? Why do a hypothesis test? Hypothesis testing is used to distinguish between two competing hypotheses. We perform the test, we come up with a probability, and that says how likely it is we would actually see one hypothesis. If we have a sufficiently large probability, we fail to reject that hypothesis. We can never prove it. We can just say we failed to reject it. If we have a sufficiently low probability, then we could say, yeah, it's too unlikely to obtain these data if this was true, so this hypothesis must be wrong. We can reject it. All right? Nice thing about these things is that we can do this statistically to get around the whole eyeball method. All right, so sometimes the eyeball method of significance works. They're clearly different. Gene's either turned on or it's turned on. That's eyeball method. But what happens if we compare bars, mean bars, and error, and with error bars on? And the bars are at different heights, so the means look different, but the error bars overlap. How do we know if it's likely that the means are different or not? Well, this is where the statistics come into play. All right? So we're going to learn how to do hypothesis testing for the rest of this course. The type of test that we run depends on the underlying data. Is it normally distributed? Is it non-normal? Are we working with binomial data? Are we working with Poisson data? Is the data a continuous variable? Is it a nominal variable? And so forth. So there's several things we have to consider that leads us down that path of what tests are available to us. And then the next part, once we know what tests are available to us, comes down to, well, what are we actually testing? Are we going to test the means? And if so, then we have this batch of tests that we run. Are we testing variance? Then we have this separate batch of tests that we can run. Or maybe we don't care about the actual mean or the variance. We just want to know direction. So is one larger than the other? Well, that opens up a different batch of tests. So to kind of introduce us to hypothesis tests and the definitions of these hypothesis tests, we're going to do this example. So roaches were captured in campus and science schools. So roaches from 2 different buildings, and then we measured their wing. All right, so question 1, just based on these data that we've collected, how many variables do we have? 2. All right, so what's the first variable? Which building? What type of data is that? It's nominal, right? It's nominal. It's categorical data. That's variable 1. What's variable 2? Wing length. Is that, what type of data is that? What interval? Why not ratio? You want it very specific. I would have just said it's quantitative or continuous data. It's continuous data. So it's ratio because you can't go below 0 for wing length. All right. But in terms of differences between analyzing ratio versus interval, there's really no difference in the tests that we perform. But if we have discrete, or if we have continuous variable, I should say quantitative data versus qualitative data, then there is differences in what tests we can run. So we've got 2 variables. We have a categorical data, so nominal data for the buildings, and then wing lengths is our continuous data. All right. The data here are in roach random data.txt. All right. I think. Yeah, it's on there. I'm just looking to see. Yeah, it's on roach data. We're gonna, if you downloaded it and we look at the data, we're gonna have the average wing length of cabinets is 7.8, the average wing length of science 3 is 6.8. So our question is, do these wing lengths differ? Well, numerically they do. They differ by a millimeter, but is that statistically significant? All right. So is this difference just dumb luck that we happen to catch smaller wing length roaches in science 3? Maybe. This is where our statistics come into play, and we'll use these a little bit later. All right, so here's our approach. We're going to assume that all of our roaches come from the same population. Right? We're going to assume that they come from the same population, which means that location designation is arbitrary. Right? That location is arbitrary. So then, if they all come from the same population, then our mean should all be equal. Right? Any differences in the mean should just be due to the random chance of getting a various sample. If we repeated it, our means could be different. If we repeated this collection, maybe cabinet's wing length is 6.8 and science wing length is 7.8. If we repeat it again, maybe they're both at 7 millimeters. Right? That's what it means when we assume that they are all in one population. If we assume that they all come from the same population, then we set up the null hypothesis, which is the main lengths are the same. Now, I say a good hypothesis, a good null hypothesis should be interesting if rejected. And that's what these no differences are. They're interesting. And it's not interesting if there is no difference. You could argue otherwise. But if we can say that they are not different, then it allows us to ask the next questions of, well, why? What is different? Which one's larger? Which one's smaller? So that alternate hypothesis is that second choice. So in all cases, our null hypotheses for all of our tests will be no difference. All right? So null hypothesis in all cases is no difference. And that would be, we could be specific. So we can say no difference in the means, or no difference in the variance. Or we can say no difference in what we expect. That's our alternate, or our null. And then our alternate will be, there is a difference. And we'll get specific with each of our tests. There we go. So how do we approach this? Well, if we assume that the null hypothesis is true, then we have what is called a null distribution. A null distribution is all of the possibilities of a test statistic that we will use to assess the validity of our null hypothesis. So if we take, for example, our wing zoom it in a little bit so everyone can see it. There we go. no difference. So if we assume the average length of Cadmus is equal to the average length of science 3, we make that assumption because we assume there's no difference. They all come from the same population. Then what we could do is take a test statistic of the difference in our means. So we go from 2 values that we're comparing to only 1. The difference in our means, this would be our test statistic. Now, if we repeat our sampling, we're going to get slightly different values for our means, which gives us slightly different values of our test statistic. What hypothesis testing is going to do is say, well, what are all the possible values that we can get for this D value? Just if we assume infinite populations, what are all the possible values? And what we would get then is a histogram of D's, where most of the D's are centered at zeros, right, with no difference, but you have the chance of getting some of these extreme values, where maybe Cadmus is larger than science 3, or science 3 is larger than Cadmus. All right? This represents our null distribution. It's all the possibilities of our test statistic under the assumption that the null hypothesis is true. And then we have an observed. This is what we actually observed. Now, the D observed, our test statistic, or the observed test statistic, is part of our null distribution. It's an entirely possible outcome. But what we're interested in is, where does our D observed fall on the histogram? Where does it fall on the histogram? Are we in the center? Are we more towards the tail? Because once we know that, then we can figure out what's the probability of getting a D observed as extreme or more extreme than this value, just by chance alone. So we're looking at our null distribution here, that histogram, to say, well, what proportion of this histogram equals or exceeds that D observed? And this area under the curve represents our probability, which is our p-value. So our p-value is the probability of getting that data as extreme or more extreme than our actual observed data if the null hypothesis is true. And that assumption, that probability, is just by random chance. What's the likelihood that we get this? We arbitrarily set our cutoff at 5%. So if this probability is 5% or less, so 0.05 or less, then we reject our null hypothesis. We say it's too unlikely that chance would give us our actual observed value. So therefore, something other than chance produced the difference. Going back to our null hypothesis, we reject it and say, look, there's no difference, or we reject the claim that there's no difference and conclude then that there is a difference in our mean. If that area, if that p-value is greater than 5%, or greater than 0.05, then we acknowledge that, yeah, chance events could have produced that. If we take a different sample, maybe we'll get a different value, maybe a value closer to the middle part of it. All right. If it's more than 5%, we basically fail to reject our null hypothesis and say, yes, there is no difference in our means. All right. This is a heavy slide. A lot of things to know. Null hypothesis, alternate hypothesis. Null distribution, our test statistic. All right. And then a p-value. Probability of obtaining data as extreme or more extreme. Assuming the null hypothesis is true.
Is this where all the definitions come into play?
Yeah, these are a big part of them. There's more. Yep. All right. So, how do we calculate these p-values? Well, in some of the tests, we can calculate the probabilities exactly. All right. And this follows like our binomial or Poisson probabilities. All right. We can easily do that. So, I don't know why that was shifted. I don't know why that was shifted. move this up a little bit. There we go. There. All right, so maybe we're flipping coins. All right, probability of flipping a head should be 0.5. All right, and when you're flipping coins and you're betting on it, right, you end up only flipping 2 heads, which means you lose money. So then you have this question: well, is this coin actually a fair coin or not? Right? Is this a coin, one of those trick coins that'll always flip, or that'll more than likely come up with tails? Well, our null assumption is that there's no difference. Our null hypothesis here is that our actual probability is 0.5. And then our alternate hypothesis is that it's not 0.5. So what we're interested in is you flip 2 heads. We want to know how likely is it to flip 2 or fewer heads, or the opposite of flipping 8 or more heads. Well, here's our curve, just to kind of demonstrate it. This curve, that's our binomial curve. That's our binomial distribution. Now I connected the lines, all right? But we have breakpoints for each number, so we can flip 0 heads, 1 heads, 2 heads, 3 heads, and so forth. So we know how to do that, and we know how to calculate those probabilities. But what we can also do is just use the p binom, just like we did p norm, to get the probability of getting 2 or less. So getting 2 and then lower dot tail equals t, so lower than that. So in this case, we didn't make any assumptions. We didn't use any sort of tables. We can calculate the exact probabilities because we can calculate the probability of getting 0 heads, 1 head, 2 head, 8 heads, 9 heads, and 10 heads. And we add them all up. That's our p-value. So exact probability tests, great. Great to use. I prefer to use them anytime anytime we can do an exact probability test. Now we'll probably come back to this, the p binomes, as part of our goodness of fit test. But I present this here to kind of get us along that pathway. Some cases you could do a complete enumeration. So I made this a little bit easier. Instead of flipping 10, we flip the coin 5 times. And what I do is you come up with every possible combination of coin flips. And our question is, if we get 4 heads out of 5 flips, is that in the realm of possibilities, or is the coin maybe not fair anymore? So if we did 4, we need 4 or more, or the other extreme, which is 1 or less. And when we add up all of our values, we have 6 of those situations out of a total combination of 32 possibilities. So our p-value then is just that proportion of our total. Again, how likely is it we'll do complete enumeration? Probably nil. We probably wouldn't do that at all. All right, but here's a situation. With this, for this example, all of these combinations, these represent your null distribution, because these are all possible combinations, assuming that the coin is fair. And then we look at those extreme values, the values that are as extreme as our observed data and more extreme. And that proportion represents our p-value. Randomization tests can also be used. So randomization tests, one that we'll use is permutation tests or Monte Carlo simulation. What this does is assumes our null distribution, or null hypothesis is true, and then generates all of those possibilities for our null distribution through randomization methods. The great thing about this is that we make no assumption about the underlying distribution of the data. All right, so even if we violate all of our assumptions, we can still do this method because our distribution reflects the underlying data. So how does this work? And this is kind of similar to what a regular like t-test or ANOVA would do. So we have our observed data. In this case, we've got 2 groups. We have measurements for each group, and in this case, I didn't list the measurements, but I list the groups. So we have 8 data points. 3 of them come from group A, 5 of them come from group B. All right? From this original data, we derive our observed test statistic, TS observed. All right, and we'll use this again. Then what we do is our first iteration. We take this classification, so you can see I've got 3 here, A is on my left, B is on my right. Take those data points, put them in a bag, all right, mix them all up, and then you reallocate them so that you have 3 on the left. Where's my cursor? 3 on the left and 5 on the right. Now, these 3 represent our first group. These 5 represent our second group. And what you see is that you will have switching of the group membership. Some of the A's become B's, some of the B's become A's, some of the A's and B's stay A's and B's. All right, but what we've done is reshuffled our data to get a new group assignment. We can then calculate the test statistic from this randomized group assignment, all right, and save it. And then we go through this shuffling and reassignment and recalculation of a test statistic over and over and over again until we get a large number of these test statistics. That's the same idea as this null hypothesis, where everyone came from the same group and our initial, or from the same population, and our initial groupings were just random samples from that population. So from here, then what we can do is create a histogram of all of the test statistic values that we obtained through this randomization procedure. All right, so here's our our histogram, and then what we would do is look at our actual observed test statistic and figure out, that would represent this blue line. We would figure out, well, what proportion of those random samples, those random test statistics, equal or exceed our observed test statistic. That proportion represents our p-value. All right. What happens if we choose not to do randomization tests? Well, we choose not to do randomization tests if we meet the assumptions of our statistical test. And those assumptions will assume that a test statistic that we calculate follows an underlying distribution. For a t-distribution, that follows a t-distribution. For a t-test, our test statistic is a t-value that is assumed to follow a t-distribution. So instead of having this nice jagged histogram, our t-distribution is very small, or very smooth. And we do the same thing. We look at our observed t-value, and we compare it to the hypothetical or theoretical t-distribution, and figure out what proportion of points lies above our observed test statistic, and that's our p-value. So here's our Roche data. All right, we're going to go ahead and load those up. And I'm going to show you we're going to learn some new functions. So, move this. Oops, I already saved that. Go File, New File, New Markdown document. Oh, is this number 8? I think. 8. All right. Hypothesis, test, and CIs. So, data. I'm going to read in my data. This is SPC, SU, data, Roche random data. I called it Roche.data. That's what I called it in this presentation, so I guess I'll do the same thing. Roche.data. Strings as factors.
How do you get it from the text file to a CSV again?
You can import the text.
But how do you get it downloaded?
Oh, just right click on the file and save link as. And it should make sure it doesn't save as an HTML. Yeah, text document. TXT will work. All right, so do this. All right, so I've read in the data. It's roach.data. And first, let's view the data. All right. First, we're going to view the data. So I've read it in. All right. The data represent two variables: location, that location, which is nominal, and wing, which is continuous. So we have two variables, one nominal, one continuous. Why did I do that? Location is the independent variable. Wing is the dependent variable. Now this is somewhat arbitrary, but this claim between independent and dependent variable is based on how we collected our data. So our focus was answering that question. Does the wing lengths differ between our buildings? So our building represents the independent variable. That's just arbitrary classification. And then what we're looking at is the dependent variable, wing length. Does wing length differ based on which building it's in? All right, so wing length, does it depend on building? That's our independent and dependent. From this, I know if we look at the independent variable, location is two levels. Let's move this over. How do I know that? Well, because in the environment it tells me that. What is that? It says it's two levels, Cav and Science 3. Location is two levels, Cav and Science 3. All right, we'll also see this on the plot and when we calculate averages. So based on our variable numbers and variable types, our planned test to perform is a t-test or ANOVA. So as you'll learn, a t-test is a special case of an ANOVA. Our p-values would be the same when we have two levels within our independent variable. Right? So I'm going to move that. So data represent two variables. All right, so the first thing we're going to do is let's view the data. Let's look at the data. So what I'm going to do is issue the plot function. Okay. We generally make a graph to look at central tendency and dispersion. That's typically what we do first. All right. The plot function allows us to do that. Okay. And plot is actually pretty good because it'll look at the variable types that we give it and automatically create the appropriate figure. So how we do it is we write a formula like that. So we're going to plot the formula y is a function of x and specify the data frame where we find variable x and variable y. Okay, so plot y as function of x. This plots y as a function of x, where the variables x comma y are found in the data frame. All right, and this is one of these things where I do not like leaving off labels when I'm making plots or doing tests that have this type of structure. So for us, we know our x. Our x is the independent variable, our y is the dependent variable. So we are making a plot of wing as a function of location, and those variables are found in roach.data. All right. And I produce this type of plot. This type of plot. All right. So this is a boxed and whiskers plot. This plots median, interquartile range, and 1.5x IQR or extreme value. All right, I'm going to leave that up there because we're going to pick this up in the lab. So the first thing, this doesn't plot the means, doesn't plot the standard deviation or variance. That's a little bit more complicated. All right, but what it does do is gives us an idea. Gives us an idea of the median. So if we assume that these are normally distributed, the median and the mean should be equal, or at least should be close to equal in a random data set. So I can look at it and say, okay, well, our means are probably located close to the medians. We can see some variation, some differences. The interquartile range gives us a measure of dispersion. We've got some overlap in our data points. Now, is that overlap significant enough to hide any true differences in our means? That's what our statistical test will tell us. So what we'll do is we'll pick up with this, make sure you save it, because this is only plotting medians. We still need to know, what our means are. So we're going to have to calculate the means, look at those means, maybe calculate some variances or standard deviations, so we can start to get a better idea of how different the means are. All right, so let me save this. All right, it's going to fail. Let me go to my network drive. And we'll pick this up in lab. For this presentation, if you look ahead, the definitions are going to be important, and then also calculating confidence intervals. So doing standard errors and a confidence interval. That's going to be the key one for us. This is R. B file. All right.